Hi and welcome to Simon Says. I'm your host Simon from CRC Robotics, and today we'll be talking about Boolean algebra and introduction to logic circuits, how to use digital systems. So, if you remember, logic is what? Zero, current, no voltage, nothing. One, there's voltage passage. But how do you use it? How can you basically play around with it without using programmation and computers? Hence the beginning. It's called logic gate. We'll start with a few of them. Here's the first one. It's called AND gate. And we'll quickly introduce another term. So here we have the A. Let's say that it's the port A. Here we have the port B. And over there we have the out. And when you're dealing with logic circuits, there's something that is called a logic table. Basically, what's coming out depending on the signal A and B. So we have the signal A, we have the signal B, and we have the out. And let's put a little bit of color to quickly understand what's going on. So remember that each input can take two values, either 0 or 1. So we put 0, 0, 1, 1, 1, 0, 0, 1 over there. So 0, 1, 0, 1. Hence we covered all four possibilities. And then we take a look at the output. Well, the AND gate, as its noun says, need to be something and something else. So that's one way to remember it, is that both need to be at 1 so that the output is 1. So if I got A0 and B0, output will be 0. A0, B1, output still is 0. A1, B0, you guessed it, 0. The last one, 1 and 1, 1 and 1, once again, then you get 1. So that's the first, it's called an AND gate. Now, we'll keep those. So we'll keep those, and we'll change a little bit the drawing over there. The next one will be called an OR gate. OR, a little like wave. Same principle. What will happen now? Why it's called OR? Well, let's go back to our logic table, shall we? So we have 0, 0. Output is still 0. We have 0 and 1. Output will be 1 because it's OR. It's one or the other. If there's 1 at 1, then the output is 1. Here, 1, 0, it's still 1. And like the AND gate, the 1, 1 combination will yield 1. Now, one of the most important gates, and often overlooked, is this one. It's called the NOT gate. You've got one input, one small triangle, and finally the output. Logic table, quickly simple. We get the A, we get the out, up, and two possible values since there's only one input. So 0, 1, the output. Not. Interesting. Let's call it the inverter if you want. If there's a 0, the output will be 1. If there's a 1, the output will be 0. To shorten out a little bit and to help, usually the symbol that you will see at NOT gate will be pretty much this one. You will see a small circle. So for example, if I was to draw an AND gate with the output inverted, well, I will have this one. Well, this one, let's say that I put 1 over there, while inside the gate it will be a 0. Let's take a look at one example of an inverted. It's called, and we'll draw it. So, okay. So, it's called that NAND gate, not AND. So we'll start by the classic AND gate. But we'll start with the classic AND gate, but we'll reverse the output and see what is going on. So we have A over there, once again B, and your classic output over there. So A be out. Classic. Once again, 0, 0, 1, 1, 0, 1, 0, 1. What's going on with the output? Well, we'll write it two ways. Let's say that we figure out this one. The black pencil will be the classic AND gate, and we'll see the NAND gate. So remember, classic AND gate was 0, 0, 0, and 1. Well, the NAND gate, since we're inverting the output, will be 1, 1, 1, and then finally a 0 at the end. Interesting. Now, sometimes you need more than one input. Than two input on an AND gate. So, well, there's two ways to take a look at it. What you could do is A, B, have an AND gate, and then the output would go into another gate. And then let's call this C. So we have a 3 AND gate that you can also draw like this. Instead of using a lot of gate, you could theoretically draw it like that. So you have a 3-way AND. The last gate I want to show you today is called the XOR gate, exclusive OR. So it goes, this is your classic OR gate with the output, but you add a little bar over there, and then you have a A, and then of course the output B, the input B, called XOR, exclusive OR. Once again, logic table 0, 0, 0, 1, 1, 0, 1, 1. If we compare it once again to the OR gate, which would be 0, 1, 1, 1. XOR 8, it's exclusive OR, so it's one or the other, but not both at the same time. So in accordance to that, 0, 0 yields 0, still is 0 on an OR XOR gate. 0, 1 yields 1, 1 in an OR gate because it's one or the other. 1, 0, logic dictates 1. Last one, 1, 1. In an OR gate it was 1, in an XOR gate it will be a 0. So now let's draw a simple circuit just to get an example and talk about synchronous and asynchronous systems to see what's going on within those gates. So let's say that we have this AND gate over there and this OR gate over there, okay? And we have two 1s over there and a 0 for example over there. So 1, 1, our output of an AND gate, we have a 1 that propagates. Here we have a 0, 0 and 1, the output is right now 1, right? So let's say that I switch A or B, what would happen? Well, down the line, if I switch A or B, the output, since this one is at 0, the output will switch from 1 to 0 because it propagates. And you can use a wide array of gates and you could put more and more and more. And this is the basic foundation of your signals. The problem, and here's the thing, is that if it's a synchronous system, okay? Asynchronous means not clocked, so no, there's no like a metronome or something that dictates when the state is switched. Well, as soon as I switch to 0 or 1, well, it's propagate immediately, so it will go really fast, and there's almost no delay, okay? This is why people, and it could lead to some kind of weird behavior at some point, so that's why people use clock system. What's going on with clock system? Well, basically what happened with a clock system is that there's a clock. Let's draw it over there. And it goes at certain frequencies. A computer clock, for example, go at 3 point something gigahertz and it's really fast. Let's not forget about that. It's not important right now. But basically, each time the clock is rising, the state from the input is computed and the output is given. So for example, if I put 1, 1 over there, well, initially the output is at 0 because it didn't get compute. Then first clock, it's up. I got my 1, my output. Let's say that in between we switch it to a 0. Okay? Then there's a new rising clock. then the output will be 0, and so on and so forth. The problem here is that when you're using clocked systems, sometimes the propagation will not go right. For example, if I'm switching both bits at the same time, let's take a look at the output. So I'm switching over there. At C, I'm passing from and I'll write it down in sequence. So I'm switching from 0 to 1, okay? So 0 to 1, at the first time it will immediately go from 0 initial state. At the next clock, it will go to 1, regardless of what's going on over there. If I was to propagate from the other way around, from this AND gate, what will happen is that, okay, I'm at 0, 1, now I'm switching to 1. Next, so I got a 0 over there, 0 over there. Then, next clock timer, it will go 1, so here there will be a 1. And then next clock, so there will be a 0. And then finally a 1. As you can see, there is some kind of 1 unit delay because there was 2 gates involved instead of just 1. So to conclude, I'll introduce the last gate, which is called a buffer. Remember the inverter? Well, if you put an inverter without the inversion, it's called a buffer, and it basically just keeps the value from one side to the other and just delay it by 1. So that you will end up having the same behavior all over again, the same number of gates. And to finalize my discussion on this, one really nice way to see that is that while it's used for logic and you can use it in electronics, the same logic applies when you're programming. For example, when you're doing if this and that this or that this, etc., etc., it's the same logic. You can actually draw this to describe your logic that you're trying to program. I'm Simon from Seriously Robotics. Thank you for listening. If you have any comments, write them below and we'll address them. Thank you.